if we take the integral around the boundary of the ball, when I don't put anything here, it means the ball is around 0. Cool. So boundary of the ball of radius r of 1 over z to the n dz, then this thing is equal to either 2 pi I if n is equal to 1 and 0 if n is not equal to 1. Okay, and this is, this can be seen in multiple ways, but it's also just an elementary calculation. So I'm going to ask you in a minute what theorems also tell us that this is the case. But for the time being, let's just calculate it. Let's create a parameterization of the boundary of the ball of radius r and see what happens. So if we let z of t be just e to the it, that's a nice parameterization of the ball. Yeah, z prime of t is equal to I r e to the it. And then let's see what happens when we do this integral. So I'm going to integrate from 0 to 2 pi, 1 over this thing, and then I r e to the it dt, just using the definition of Contour integration. So then we have a fair bit of cancellations here, right? So what are we going to have? We're going to have, let's pull out the I straight away, and then we're going to have, let's actually pull out also the R, because it's not involved in the integration itself. So let's pull out the I, and then we have R to the 1 minus n here. That looks very bad. Do that again. So I to the R to the 1 minus n. Looks slightly better. And then what do we have? Then we have just e to the it to the power of 1 minus n. So 1 minus n like this. dt. This is what we have. Yeah? Everybody happy? Yeah? Let's continue it down here. So then what's this? This is equal to I r to the 1 minus n. And if we just expand this out, we know what e to the I whatever is. So it's equal to cosine of it 1 minus n plus, oops, not it, cosine to the t times 1 minus n plus I sine to the t times 1 minus n dt. Yeah? And if n is not equal to 1, then this thing is just some function which is periodic from 0 to 2 pi. Yeah? If n is any number except 1, then this thing is just a nice periodic function from 0 to 2 pi. And when we integrate it from 0 to 2 pi, since the antiderivative is periodic, it just is 0, and the same is true for this. Do you see what I mean, people? Yeah? Everybody give me a thumbs up, or if you see what I mean. Okay. Okay, cool. So then everything here just vanishes. So this is just 0 if n is not equal to 1. And on the other hand, if it is equal to 1, then what happens? Well, then this thing is 0. This thing is cosine of 0, which is 1, right? And this thing is just sine of 0, which is 0. So if n is equal to 1, then let's call this thing star. Then what is star? It is just equal to well, this part here is just going to be I times r to the 0, so it's just going to be I. And then this thing here is just 1, and then plus 0 times I. So it's just 2 pi I, and that's it. So that's our claim right here. That's our claim right here. Yeah? Cool. All right, so why did I take you through this? Well, let's see what happens if we have a function with a pole. Yeah? If we have a function with a pole, then our theorem is that we can write it in this form like this. Yeah? And then let's take our function with a pole and let's integrate a little circle around z0 itself. Okay? We make the circle small enough so that it's within the radius for which this representation holds true. Yeah? Okay. Now I'm going to raise the board. I want you people to think about what will be the integral of a function f, which has a pole and therefore is representable this way, when we integrate it around the little ball of a small radius around z0. Yeah? Think about that while I raise the board, and then tell me about it when we're done. Okay, so if we have a pole at z0, and so we have this representation locally around z0, so the small ball, the sum from k is equal to 1 to n of a to the minus k, z to the minus z0 to the minus k, and then the next part is holomorphic, so I'm just going to write, okay, let me write it as an expansion to begin with. The sum from k is equal to 0 to infinity ak z minus z0 to the k. And so let's draw a picture. So we have our domain. We have some point here where f actually has a pole, and we're taking a little tiny radius around this thing. This is z0. Tell me about what this thing will be. So if we integrate around the boundary of the ball of radius r around z0 of f of z dz, tell me about this. Don't have to tell me everything, but tell me what you know, given that we have this representation. In what ways do we have a simplification of this thing? Perfect, yeah. Perfect, yeah. So we can just break this up into this thing, the sum k equals 1 to n. Let's take out the coefficient a to the minus k, why not? Integrate around this thing, z minus z0 to the minus k, dz plus this thing here, this part here. Yeah, and exactly as Jaime said, this thing here, if we do a change of variables and rescale it so that z0 is not rescale, but reposition it so that z0 is 0, then it's exactly the integration we had before, right? Or you don't even have to do that. If you just create your parameterization, then it's exactly the same parameterization, except it's z of t is r e to the it plus z0, and the same thing happens, same calculation happens, right? So we know that everything here will cancel except the term when k is equal to 1, yeah? And when we have k equals 1, then this integral just becomes 2 pi I, yeah? And this thing is just holomorphic. It's just holomorphic. It's a little ball where it's holomorphic, so just by Cauchy's theorem, this thing is equal to 0. Yeah? Or Goldstadt's theorem, I should say, in this case. Yeah? So the only thing that survives from here is just 2 pi I a to the minus 1. Yeah? Which is pretty extraordinary. So we have this integral around this little ball, and the only thing we have to care about is just what the coefficient a to the minus 1 is. And it's extraordinary because if instead of integrating around a little ball, suppose we integrated around a closed curve, which just contained one pole, and that one pole is z0. Yeah? Yeah? Then I claim that the integral around this closed curve gamma will also still just be this thing. Now tell me why. Let me write that down and you give me an explanation. Suppose gamma is a closed curve, or a simple closed curve, which contains only one zero. Sorry, which contains only one pole. Then I claim that the integral around gamma of f of z dz is still 2 pi I a to the minus 1. Tell me why. This was something, this is some principle that we've used, and on reading some of your homeworks and also your exams, not all of you are that comfortable with this. This is one of the basic things we use to simplify life when we do contour integrals. And we've used it a fair number of times. So what thing can we do to make our life easier when we have a contour integral? Remember how we proved Cauchy's integral formula? Yeah? We had some point in the center of this closed curve, which we're integrating around, right? But we don't actually want to deal with that contour. We wanted to deal with another one, yeah? Yeah? We wanted to deal with a little ball, the boundary of a little ball around that particular point. And we're able to reduce it to that situation, right? Because what did we do? How do we do it? What do we use? We used the keyhole contour, and how did it work? Why were we allowed? So let's blow up this thing here. Let's blow it up to this scale. So we have Z0 here, and this is some closed curve, gamma. Yeah? Just like in the case when we had Cauchy's integral formula, we're able to reduce the integral around this closed curve to the integral around a little ball, like this. Yeah? And as you say, we use the keyhole contour. Yeah? So a keyhole contour is when we make a little break like this, and then go down, up. So if we put the parameterization, we go around like this. Always anti-clockwise. Yeah. And how did this work? How did we reduce the integral around gamma to the integral around the boundary of the ball? What was the theorem we used there? So one of the reasons I emphasize to you that I want you to understand and study and be very able to recall the proofs is that the proofs have these key methods that are used over and over again. And if you account with these key methods, then many of the theorems just fall out rather naturally, and this is one of them. So think about how we did this. How did we reduce the integral around the outer contour gamma to the inner one around the boundary of the ball? So Jamie's right, Hamid's right, that we had the cancellation here on this little hole part connecting them, yeah? So ultimately that thing becomes unimportant. So that when we take the limit of this thing as the hole goes down to 0, it just becomes the integral around this thing. But if we look at this guy here is actually going clockwise around the circle, yeah? So then as we let the whole thickness get thinner and thinner in the limit, this integral just becomes the proper anti-clockwise integral around the outer curve minus the anti-clockwise integral around the inner circle. Yeah? And what we want to do is say the integral around the outer curve is equal to the integral around the inner circle, which would mean that entire expression is 0. Yeah? So why do we know that entire expression is 0? Think about our context. We have a function f. It has only one pole and has no other singularities. Just got one pole here at z0. Yeah? So let's call this keyhole contour here. Let's call this keyhole contour pi of delta, where delta is the thickness of the little hallway here. Yeah? So let's call this thing pi of delta. Tell me what this is. What is the integral of pi of delta f of z dz? Why is it 0? Yeah, Cauchy-Gorstadt's theorem, yeah? Because this thing here yeah, is contained within what I called a dyadic good region, right? Where we have an actual antiderivative. Yeah, that's exactly how we proved Cauchy's integral formula. Cauchy's integral formula, we had some expression like this, f of zeta minus z, which was nicely holomorphic except at z itself. So we did a keyhole excluding the z, yeah? And then we had that the integral around this keyhole contour was equal to 0 because this function has a nice primitive on this dyadic good set that contains this keyhole contour and its interior. Yeah? Is that coming back to you? Give me a thumbs up if it comes back to you. Okay, good. So what this is the principle of deformation of curves, that if we have some complicated curve, yeah, but we can create some keyhole contour to reduce it down to some simpler curve just by having that the keyhole contour has its interior and its closure on a set where the function is nicely holomorphic. If that's the case, then we can just apply the fact that we have a primitive and this thing has to be equal to 0 for every thickness delta of the hallway. Cool. All right, so we have that this is equal to 0. Yeah? This is equal to 0. And if we let delta go down to 0, then exactly as we've seen before, the sides of the hallway will cancel each other out. Yeah? So this is true for all delta bigger than 0. So taking the limit as delta goes to 0 of this thing, of z dz, we did this somewhat carefully before. We saw that this thing cancelled. This is equal to the integral around the outer contour, this thing, minus the integral around the boundary of the ball of radius z0. Huh? Like this. Yeah? So in particular, the integral around the outer contour just reduces down to the integral around the boundary of the ball. And we can make the ball as small as we like. Yeah? And we call this the principle of deformation of curves, that whenever you have a curve, you can just reposition it around whatever interesting thing is happening that you actually want to understand. Yeah? And that makes these calculations very much simpler. And that's how we're able to prove Cauchy's integral formula, because this expression is hard to understand, except when we go on a very small ball, and then it becomes rather easy to understand just by differentiability. Yeah? Because by differentiability, we know what f looks like. It looks like its tangent plus some higher order terms. And then we can calculate this expression rather easily. Yeah? Cool. All right. So whenever you have a homework problem or any kind of problem involving doing some integration, think about deforming the curve to a more convenient curve by creating a keyhole contour where on the interior of the keyhole contour, your function is actually holomorphic on the interior and on the boundary. Yeah. And that'll save you some work. All right. And in this particular case, I claim that we can actually reduce the integral of this closed curve here down to this thing. It follows exactly from this calculation, right? So we know that this thing is equal to 0. So the integral around this contour f of z dz is just the integral around the little small ball. And that thing is indeed what we've just calculated, 2 pi I a to the minus 1. So this is super powerful. This holds true for any closed curve containing z0, which is to me was very, very striking and very almost hard to believe when I first saw it, because obviously you have completely different curves. I mean, it's a totally different situation in real analysis of real valued functions from the real line because if you change your domain, you obviously get your completely different integral. Yeah, integrate over a different set, you get a completely different integral most of the time, unless the function is identically 0. Yeah. So here we have a non-trivial function, but we can have any closed curve we like, and we get exactly the same answer out. Exactly the same answer out. It's quite a shocking result in lots of ways. Yeah? So yeah, this is the start of so-called residue calculus, which allows us to explicitly calculate many integrals by this principle. And this principle is actually rather simple. So shocking though this result is, the principle is rather simple. We haven't actually had to prove very much. All we've proven is this thing, which is just elementary, right? This doesn't take long to prove. Do it for yourself. It'll take less than 2 minutes, right? Just from the fact of the definition of a pole. Yeah, this is just trivial. Well, not trivial, but this is rather quick. Yeah? And then the second thing we've proven is that if we integrate 1 over z to the n, yeah, it's either equal to 0 if n is not equal to -1, if n is not equal to 1, or it's equal to 2 pi I. That's the only other thing we proved, and that's an elementary calculation too. Those two things together imply this, plus the Keyhole Contour principle, plus the deformation of curves principle. Yeah? Imply this strikingly strong result. Another thing to say, I didn't fudge anything here. I didn't do any funny swapping of limits underneath integral signs, because when I do this, here I have just a nice finite thing. It's just a finite collection of terms. Yeah? So I can indeed break it up into the sum. And this thing here, which is the infinite sum, I'm just considering as a holomorphic function. I'm not passing the integral through. I'm just applying the fact that this thing is equal to 0 just by Cauchy-Gorstadt theorem. Yeah? So this is completely rigorous. I'm not fudging any technical details. Yeah? So this remarkable result really does follow very, very easily. It's a very, very easy result. All right. Now, tell me what you expect to happen when we have a more complicated situation. What about this? What about if we have numerous poles, say Z0, Z1, Z2, Z3, Z4. All of these guys are poles. Yes, I know what you're saying, but it's not. It's the same keyhole, but we're going to. Yeah, I know exactly what you're saying. It's the same contour, but we have multiple keyholes going around these things. So we go down, put a little thing like this, yeah, and then something like this, and then something like this. Did this wrong. Something like this, and then a guy like this. Yeah, and that is how we're going to break up this integral. And then the same principle will apply, right? The same principle will apply. So, did I do this wrong? Yeah, I did it wrong. Like around this way. And then like this way. All right, so tell me what will happen then if we have, let's not make it 4, let's make it n. Suppose not n, let's make it p. We have p poles inside of our contour here. What will this integral around this curve reduce down to in that case? Yeah. I see exactly what you're thinking. I understand why you hesitate for a second. So actually, I don't like the index p anymore. Changed my mind, calling it m. I've learned recently that many foreign mathematicians call pi p. And some French guy justified this to me, saying that that's the Greek pronunciation. So that was interesting. That leads to confusion with the letter. So let's call it m. Okay, so if we do this, then sure enough, it's going to reduce down to the integral of around these m individual little balls around the singularities, yeah? So we're going to take the sum from k equals 1 up to m around the integral, and on each one of these guys, we're going to take some radius which is small enough so that it's within the radius for which we have this kind of expansion, and therefore we have that the integral around this boundary of the ball turns out just to be this very simple expression given by 2 pi a to the minus 1. But there's a caveat. So let me write this and then tell me how I should write the next thing. So since they're finitely many, we can choose the same r, which is small enough for all of them. That thing won't be a problem. dz, so this is just the contour principle, well, definition of curve principle, I should say. And then this thing reduces down into something simpler. But tell me what I should write here. Tell me what I should write here. I mean, you said it before. Well, you said, tell me what you think I should write here. Perfect. That's exactly the caveat. We have to think a little bit carefully because each one of these things here, we can calculate depending on the expansion we make around this pole. Right? We made the expansion around the pole in this thing here. So this is only true in a small radius around Z0. Yeah? And the coefficients here depend on the expansion. Yeah? So this coefficients here depend on the fact we're expanding our function around Z0. And around Z1, we'd have a different expansion with different coefficients. Yeah? Yeah? Key point. So it might be tempting to write a to the minus 1, but as you hesitated because you're aware that for different points, then we're going to have a different a to the minus 1. Yeah? So we need a better notation for this a to the minus 1 term. Yeah? We need a better notation, and that motivates the concept of residue. So here I don't have a good thing to write because I don't know how to write a to the minus 1 in a way that indicates it's around each one of these things. I haven't got a notation for it yet. So therefore we need a notation for it, which is the concept of residue. So definition. The residue of f at pole, so I'm going to call it Z0, but it's not this Z0, it's any Z0, which we write like this, res Z0 of f is equal to a to the minus 1, where f has the expansion f of z is equal to the sum k is equal to 1 to n, a to the minus k, z minus z0 to the minus k. And now I'm just going to write h for the holomorphic part like this. Okay. So this definition is convenient for us because, or it's useful for us because it specifies that we're talking about the a to the minus 1 at this particular point where we have the pole. Yeah? And that's what we need in order to write something meaningful here. So we write this. We write the residue of at zk of f. And that's all that residue means. Yeah. So when I first saw it a long time ago, I thought this is a kind of complicated expression, but no, it's not. It is just that we want some notation that allows us to specify what a to the minus 1 coefficient we're talking about when we have a bunch of separate different poles. Cool. So that's an even more extraordinary result. So it means that if we have a function that just has a collection of poles inside our contour, then all we need to do is this finite addition of just what the residues are at the individual poles. And that is the so-called residue theorem. That's the residue theorem. And that's one of the most striking and deepest theorems in the subject. And it's one that has enormous power, as we're about to see. Okay, let me raise the board. Okay, so let's write what we've learned as the theorem. Suppose f from omega into c is such that for simple closed curve gamma, we have that f has only finitely many singularities Z1, Z2, up to Zm. So int is the interior of the simple closed curve, and f is hollow on the closure of the interior of the simple closed curve. Take away these finitely many points. Which means it's holomorphic on some open set that contains the closure of the interior, subtract this finitely many points. Then integral around this thing is the sum from k equals 1 up to m of 2 pi I, the residue at zk of f. Cool. So that means that in order to calculate a whole wide, massive class of integrals, all we need to do is to calculate residues. Yeah? We need to calculate residues. Yeah? And this is almost as good as it gets, because if there is no singularities inside the closed curve, then as you know, the integral is 0. So if we get anything non-trivial at all, we're going to have some singularities. Yeah? Yeah? The specification is that we want finitely many of them, and we want them to be poles. We don't want them to be essential singularities.